Class 12th, subject physics, 6th chapter, superposition of waves. From the chapter, let us see numericals from exercise. Let us see the numerical number 18. It is given as a pipe open at both ends has a fundamental frequency of 600 Hz. The first overtone of a pipe closed at one end has the same frequency as the first overtone of the open pipe. How long are the two pipes? So, in this case, the given data is the fundamental frequency for open pipe NO equal to 600 Hz. Then the given condition is the frequency for first overtone in case of closed pipe equal to frequency of the first overtone for open pipe. That is NC1 will be equal to NO1. Velocity of sound phi is equal to 330 meter per second. And then we will have to find out the length of open pipe LO and the length of closed pipe LC. So we know that for an open pipe, the fundamental frequency for any open pipe, the fundamental frequency NO is given as phi upon 2 LO. NO equal to phi upon 2 LO, and therefore length of open pipe will be LO equal to phi upon 2 NO. LO equal to phi upon 2 NO, that will be equal to 330 upon 2 into 600, which comes out to be 0.275 meter. So length of the open pipe will be equal to 0.275 meter. And therefore for this open pipe, frequency of the first overtone is 2 NO. 2 times NO, that will be equal to 2 into 600, that is equal to 1200 Hz. 1200 Hz. Now for pipe closed at one end, for the pipe which is closed at one end, the frequency of first overtone is equal to 3 phi by 4 LC. The frequency for first overtone will be given as 3 phi upon 4 LC, and therefore we can write by the given condition 3 phi by 4 LC must be equal to 1200. That is the frequency for the first overtone in case of open pipe, and therefore we can write LC equal to 3 phi upon 4 into 1200. LC is equal to 3 phi upon 4 into 1200, that will be equal to 3 into 330 divided by 4 into 1200. Calculating this, we will get 0.206 meter, and this will be the length for closed pipe. Length of the closed pipe equal to 0.206 meter. Now we will go for next numerical, that is question number 19, in which it is given that a string 1 meter long is fixed at one end. The other end is moved up and down with frequency 15 Hz. Due to this, a stationary wave with 4 complete loops gets produced on the string. Find the speed of the progressive wave which produces the stationary wave. Then hint is given that remember that the moving end is having antinode at that point. The moving end is an antinode. and therefore in this numerical number 19 the given data is length of the string L is equal to 1 meter, frequency N is equal to 15 Hertz, and we have to find out velocity phi of that progressive wave. Now in this case, as per given data, we can write total length L will be equal to L by 4 plus 4 into lambda by 2. L is equal to L by 4 plus 4 into lambda by 2, and therefore it will be equal to 9 by 4 lambda. 9 by 4 lambda, and therefore lambda will be equal to 4L by 9, 4L by 9, which will be equal to 4 into 1 by 9. That will be equal to 4 by 9 meter. Therefore lambda is equal to 4 by 9 meter, and now phi will be equal to n lambda. Phi is equal to n lambda. Therefore phi is equal to 15 into 4 by 9, 15 into 4 by 9, which comes out to be 60 by 9, that is equal to 6.667 meter per second. 6.667 meter per second. This will be the velocity of the progressive wave. Now let us see numerical number 20, which is stated as a violin string vibrates with fundamental frequency of 440 Hz. Then what are the frequencies of first and second overtones? And therefore for this numerical, the fundamental frequency NF is given as 440 Hz. Then we have to find out the frequencies for first and second overtone, that is N1 and N2, that we will have to find. Now for first overtone, we are having frequency N1, that is equal to 2 NF. Frequency N1 is equal to 2 NF because all the harmonics will be present in this case, and therefore frequency of first overtone N1 equal to 2 times the fundamental frequency, which will be equal to 2 into 440, which comes out to be 880 Hz. So N1 is equal to 880 Hz. Now for second overtone, for this second overtone, N2 is equal to 3 NF. N2 is equal to 3 NF, and therefore we will get 3 into 440, which will be equal to 1320 Hz. 1320 Hz. So these are the frequencies for first and second overtone, that is 880 Hz and 1320 Hz respectively. Now let us go for next numerical, that is numerical number 21, which is stated as a set of 8 tuning forks is arranged in a series of increasing order of their frequencies. Each fork gives 4 beats per second with the next one, and the frequency of the last fork is twice that of the frequency of first. Then calculate the frequencies of the first and last tuning fork. And therefore in this case the given data is the frequency of 8th tuning fork N8 is equal to 2 N1, that is frequency of last tuning fork is equal to twice of frequency of first tuning fork. That condition is given. Similarly bit frequency is given, that is equal to 4 Hz, that is the frequency difference between successive tuning forks will be equal to 4 Hz, and then we will have to find out the frequency of first and last tuning fork, that is N1 and N8. Now in this case, as forks are arranged in increasing order of their frequencies, as the forks are arranged in increasing order of their frequencies, therefore we can write N2 is equal to n1 plus 4 as bit frequency is 4. Similarly, n3 will be equal to n2 plus 4, which will be written as n2 is n1 plus 4 and again this 4, so that n1 plus 8, that will be written as n1 plus 2 into 4. n1 plus 2 into 4. Similarly, n4 will be written as n3 plus 4, but n3 is nothing but it is n1 plus 8, and therefore if it is n1 plus 8 and plus 4 is there, that will be equal to n1 plus 12, which will be written as n1 plus 3 into 4. n1 plus 3 into 4, and therefore for last tuning fork n8, we can write it as n7 plus 4. n7 plus 4, that will be equal to n1 plus 7 into 4. n1 plus 7 into 4, that will be equal to n1 plus 28. n1 plus 28. Now, since n8 is equal to 2n1, n8 is equal to 2n1, therefore 2n1 is equal to n1 plus 28, because this n1 plus 28 is the value of n8, and therefore 2n1 equal to n1 plus 28, therefore n1 is equal to 28 hertz. n1 equal to 28 hertz, and therefore n8 will be equal to n1 plus 28, n8 equal to n1 plus 28, that is equal to 28 plus 28 is equal to 56 hertz. So the frequency for first tuning fork comes out to be 28 hertz, and for the last is 56 hertz. And now let us go for next numerical, that is numerical number 22, which is given as a sonometer wire is stretched by tension of 40 Newton. Then it vibrates in unison with a tuning fork of frequency 384 Hz. Then how many numbers of beats get produced in 2 seconds if the tension in the wire is decreased by 1.24 Newton? And therefore for this 22 numerical, given data is T1 equal to 40 Newton, that is the initial tension. Then N1 will be equal to 384 Hertz. Then tension T2 will be decreased by 1.24, therefore it will be 40 minus 1.24, that is equal to 38.76 Newton. And we have to find out number of beats produced in 2 seconds. Number of beats produced in 2 seconds. For that we are having the expression for fundamental frequency of vibrating string, that is n is equal to 1 upon 2l square root of t by m. N is equal to 1 upon 2l square root of t by m, and therefore we can write the formula for n1 and n2 as n1 is equal to 1 upon 2l square root of t1 by m, and n2 is equal to 1 upon 2l square root of t2 by m. Only tension are different, L and M will be kept constant, and therefore taking ratio of N2 and N1, we can write N2 by N1 equal to square root of T2 by T1, as N is directly proportional to square root of T, and therefore we can write N2 upon 384, N2 upon 384 equal to square root of 38.76 divided by 40. 38.76 divided by 40, and therefore we will get N2 upon 384 equal to square root of 0.969, square root of 0.969, which comes out to be 0.9844, 0.9844, that will be the value of N2. And therefore N2 by 384 is equal to 0.9844. Therefore, N2 will be equal to 384 into 0.9844. 384 into 0.9844, that will be equal to 378 Hertz. 378 Hertz, and therefore we can find bit frequency, that is difference between N2 and N1, that is N2 minus N1 will be equal to 384 minus 378, that will be equal to 6 Hertz, and hence these bits will be produced per second. Therefore, number of bits in 2 seconds will be equal to 2 into 6, that will be equal to 12 Hertz. So, number of bits produced in 2 seconds will be equal to 12 Hertz. Now, let us go for next numerical, that is numerical number 23, in which it is given that a sonometer wire of length 0.5 meter is stretched by a weight of 5 kg. The fundamental frequency of vibration is 100 Hz. Calculate linear density of wire. Calculate linear density of wire, that is its mass per unit length. And therefore, for this 23rd numerical, given data is L is equal to 0.5 meter, tension T is equal to 5 kilogram, that will be equal to 5 into 9.8, that is equal to 49 Newton. Then frequency N is given 100 Hertz, and we have to find out M, that is linear density of the string or its mass per unit length. Again, we are having the formula for fundamental frequency of vibrating string, that is N is equal to 1 upon 2L square root of T by M. 1 upon 2L square root of T by M. Squaring this, we will get N square equal to 1 by 4 L square into T by M. N square equal to 1 upon 4 L square T by M, and therefore from this M will be equal to 1 upon 4 L square T by N square. 1 upon 4 L square into T by N square. Now putting the values, we will get M is equal to 49 upon 4 into 0.5 square into 100 square. 49 upon 4 into 0.5 square into 100 square. If we calculate this total, then we will get 4.9 into 10 raised to minus 3 kilogram per meter. 4.9 into 10 raised to minus 3 kilogram per meter. This will be the linear density of that given string. And now we'll go for next numerical, that is numerical number 24, which is stated as the string of a guitar is 80 centimeter long and has fundamental frequency of 112 Hz. If a guitarist wishes to produce a frequency of 160 Hz, then where should the person press the string? So where that string must be pressed by that guitarist, that we will have to find out. And therefore for this, given data is length L1 will be equal to 80 centimeter, then corresponding frequency N1 equal to 112 Hz, then N2 is equal to 160 Hz, and the respective length L2 that we will have to find. And therefore we know that according to law of vibrating length of the string, so by the law of vibrating length of the string, that is NL is equal to constant or N1 L1 equal to N2 L2. As NL is equal to constant, therefore we can write N1 L1 equal to N2 L2, and therefore L2 will be equal to N1 L1 upon N2. L2 will be equal to N1 L1 upon N2. putting the values we will get 112 into 80 upon 160. 112 into 80 upon 160. Calculating this, we will get 56 centimeter as L2. That means that guitarist will press that string at a length equal to 56 centimeter. So that will be the required answer.